Those who are online, am I audible?
Yes, sir.
Yeah. Shall we get started?
Yes, sir.
Okay. Are you able to see my screen?
Yes, sir.
Okay. Just right. So, in the previous class, we discussed some terms related to magnetic field, right? So, what were the eight terms that we discussed? Can you tell me? What were the 8 points, to be more specific? I'm not going to go through everything, but there's the outline that we are going to summarize and then start with. So, first we understood what is a magnetizing field. Then, so can you tell me what is a magnetizing field? So when you take a magnetic substance, and place it in the presence of magnetic field, this will magnetize the magnetic substance. So the amount of strength that this is going to exert is what is called as the magnetizing field. So magnetizing is input or output? It is a input, right? What is the output? By using a magnetizing field, what are we going to have? So we'll have magnetic induction. So basically, what is magnetic induction? Magnetic induction is a combination of magnetic induction is a combination of which two? It is a magnetic field due to the magnetic field produced due to the current in the wire plus the induced magnetic field. You remember that? Then, so this is the mathematical expression, if you remember, mu naught into n into I plus mu naught into n into Im. So what is n into I? It has a name. It is the number of the ampere turns per unit length. This is given a name called as magnetizing field, intensity of the magnetizing field. That is written as capital H. What is this N into Im called as? It is a intensity of magnetization. Magnetization is the output. Magnetizing field is the input. So mu naught into H plus mu naught into M. Right. So that's what we have seen here. What is N into I? It is capital H. Similarly, what is intensity of magnetization? The basic definition of intensity of magnetization is capital M is equal to the amount of dipole moment developed per unit. Correct. The amount of dipole moment developed per unit volume. But how is it mathematically written as? It is written as small n into Im, where small n is going to be the number of turns per unit length multiplied with Im. What is the Im? It is called as the magnetization surface current. Right? So after this, what did we see? You remember this expression mu naught into H plus M? Right. Then we saw the concept of what is magnetic permeability. So what is magnetic permeability? The extent to which the substance is allowing or the substance is able to get magnetized is what is called as magnetic permeability. And how is it defined as? It is defined as a ratio of B by H. What does B stand for? Magnetic induction. Magnetic induction divided by what does H stand for? Intensity of magnetizing field. So it is B divided by H. After this, what did we see? We saw relative permeability. Relative means you compare with one of the known quantities. So how is it written as? Relative permeability is represented by the symbol mu r. You write it as mu divided by mu naught, right? Then there is something called as magnetic susceptibility. It is defined as the ratio of intensity of magnetization to the intensity of magnetizing field. So it is capital M divided by H, output divided by input. So susceptibility is something similar to efficiency, how efficiently the material is able to get magnetized, right? And what was the last relation that we saw? Relation between magnetic permeability and magnetic susceptibility. So what is it? Mu is equal to mu naught into 1 plus chi m. This is the relation between magnetic permeability and magnetic susceptibility. What does this stand for? Mu r is equal to 1 plus chi m. This stands for the relation between relative permeability and the magnetic susceptibility. So with these concepts, right, with these terms that we have used, we are going to understand the concept of paramagnetic, diamagnetic, and ferromagnetic substance, for which, if you remember, I showed you a video in the, I think it was last week, no? Last Wednesday we saw. But what we'll do is, just for the sake of revision, we'll just have another look at it, and then we'll understand how the table is formed. You are going to tell me by looking at the notes. Is the point clear? Is the cursor there? Ah. So we saw this in the last week, right? Yeah, observe this. So what was this experiment all about? So this,
this is a new and different category of magnetism called either para or diamagnetism. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed.
what is this property called as? The property of the magnetic retaining magnetism even after the magnetic substance magnet is removed, or the magnetic field is removed. It has a name. It is called some property. I told this word. What is it doing? It is retaining magnetism. No? This is called as retentivity. So what do you mean by retentivity? Retaining magnetism even after the removal of external magnetic field. Is the point clear? Right.
Paramagnetism is a similar effect, except that it's much weaker and temperature. Aluminum is a good example of paramagnetism.
So only thing is, there are many materials that he has. You need to observe whether it is getting attracted or repelled. If it is getting attracted or repelled, how fast or slow it is getting attracted or repelled. If you know that, we can prepare the table for it. So if you observe, aluminum is actually getting attracted. What about a ferromagnetic substance? If you take a nail, is it going to get attracted or repelled? This is South Pole, attracted. North Pole, attracted. So ferromagnetic substance, irrespective of whatever pole you are going to bring close to it, it is going to get attracted only. The same is going to be with respect to the paramagnetic substance also, but the only difference is going to be the strength with which it is getting attracted. So in the case of a paramagnetic substance, you saw the way it was turning. Is it coming faster? It's not ready to get combined. It is only coming in a slow way, means the magnet is able to pull it. So it is getting attracted. So paramagnetic substances and ferromagnetic substances exhibit similar kind of a property, except the fact that ferromagnetic substances are going to be more stronger and the attraction will be more strong, whereas a paramagnetic substance will have feeble attraction. It is a little weak, right? Like how it is happening here. Then what about a diamagnetic substance? So what is the example? Out of all the materials that you're able to see here, which material exhibits diamagnetic property? That was the first thing he showed. It was water, right? So those who attended that class, can you tell me what is the reason for paramagnetism in a material to exist? What is the reason? Why is it? So because when you look at aluminum, what is going to be the valence electron? Basically, what is the electronic configuration? 2, 8, and 3. So out of the 3 electrons which are there in the valence shell, how many will be paired? 2 will be paired and 1 will be unpaired. It is because of that unpaired electron, aluminum is actually exhibiting paramagnetic properties. Then what about a diamagnetic substance? Diamagnetic substance have no unpaired electrons, mean everything is paired. If you take water, so you have 2 lone pairs. Lone pairs means already they are paired together, no? So since there are no unpaired electrons, water exhibits the property of diamagnetism. So just to conclude, paramagnetic substances should have unpaired electrons and diamagnetic substances should have paired electrons. Okay.
So is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cuprous sulfate are good examples of paramagnetic substances. Cuprous sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnet. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or anything. Graphite is repelled by a magnet, always, both by the north and south. Pyrolytic graphite is a growth crystal of flat carbon layers, which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present.
I told this concept has a name. Superconductor is over. Okay. See, bottom you have the superconductor. When a magnet is kept on the top, it is neither going down, it is not flying away also. It is actually levitating there. That has a name. What is the name I told you?
Magnetic levitation.
Magnetic levitation. It's called magnetic levitation. That's so this is the principle used for designing the trains and all, the bullet trains and all. They use this concept. Because when you think of friction, right, friction will have wear and tear. Whereas this one, when you use it for the brakes, you will not have wear and tear. And at the same time, you can maintain more speed also. Okay.
Perfect diamagnet. The most famous and powerful diamagnetic is bismuth, element number 83 of the periodic table.
I hope you could understand, no?
One way to check whether an object is diamagnetic or paramagnetic is to know the line of magnetic.
So listen to this.
Diamagnetic objects like glass. Here, see that the glass is diamagnetic.
Listen to this. Apart from understanding this concept practically, it is important for your exam also. They'll give you a diagram and ask you, with this orientation, tell whether the material is a paramagnetic or a diamagnetic substance. So what will happen? Can you guess? This paramagnetic substance, till now, with whatever you saw, is a paramagnetic substance responding to magnetic field or opposing it? It is responding, it is getting attracted. Suppose this material which is suspended, had it been a paramagnetic material, right? Imagine this is the North Pole, this is the South Pole, right? So had it been a paramagnetic material, then in which direction will that material align itself? Tell me one thing, is it going to be in, I'm not asking whether north to south or south to north, forget about it. Is it going to get aligned along the magnetic field or perpendicular to magnetic field? Listen to my question carefully. It is a, what kind of substance it is? A paramagnetic substance. This is North Pole, this is South Pole. There is a magnetic field going from north to the south. You're able to visualize, no, that there is a magnetic field here. You suspended a paramagnetic substance. Will it turn itself? Okay, let's say you suspended it like this. Okay, let's say, is it going to get aligned like this in the direction of magnetic field or perpendicular to it? It will get aligned. Is the point clear? You think logically, see, ferromagnetic and paramagnetic have similar properties. They both attract, right? Imagine this is the ferromagnetic substance. Had I suspended, see, if the north pole is here, south pole is here, I suspended it like this. I suspended this magnet between another magnet where there is a north pole here, south pole here. What would have happened? It would have aligned itself in such a way that if this is north pole, then which pole of the magnet will come closer to this? South pole. Similarly, the north pole would have been on the other side. Am I clear with that point? In a similar way, paramagnetic substance will also align along the direction of magnetic field. But diamagnetic is not responding to the magnetic field. So it should start aligning itself in the direction perpendicular to the magnetic field. So we have glass here. Is glass a diamagnetic or a paramagnetic substance? Let's check and see.
Diamagnetic, sir.
By looking at it, tell me. It's a diamagnetic. What is this? Aluminum. Is it aligning itself along the direction of magnet? That's all. Are you able to understand? So now the logic makes sense, right? It should work like that.
Paramagnetic diamond. You have to know what the electrons are. Consider, for example, we see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet.
Okay. So now try to understand. We'll connect all the dots that we discussed from the beginning. Okay. See, in the beginning of this chapter, I told you one thing. What is the reason? What is the reason for a material to have or exhibit magnetism? It is because of the electron revolving in an orbit. So here what is happening is, there is an unpaired electron which says, I'm ready to get magnetized. So that is why this unpaired electron is actually responding to the external magnetic field, as a result of which it is getting attracted. Whereas when you talk about a diamagnetic substance, you don't have this, rather you have only this pair. So the magnet does not know which electron to be magnetized. That is why it is not responding to the magnetic field and it is always trying to repel it. Makes sense? Are you able to understand the logic? See, these kind of questions might be framed in the assertion reason part. So you should be able to answer it. Am I clear with that? Right?
What about a diamagnet like water? Yes, the water molecule. It has all its electrons here. It will not be magnetized. In fact, water is repelled by magnet. The electrons move to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
Is that clear? So having this in mind, now immediately we can jump to this topic. I think you yourself will be able to answer it. Okay. Right. So when you look at this table, no, we are going to see the property and how this property is exhibited by a diamagnetic, paramagnetic, and a ferromagnetic substance. Let's go one by one. Okay. First question is, yeah. So the first question is effect of magnets. So when you take a diamagnetic substance and place it in the presence of an external magnet, how will it respond? It will repel. But is it going to repel faster or slowly? So there is a feeble repulsion. So can I say that they are feebly repelled by the magnets? But what about a paramagnetic substance? They are attracted, but there is a feeble attraction, right? But what about a ferromagnetic substance? They are attracted strongly. So they are going to get strongly attracted by the external magnets. Am I clear with that point? Second, See, effect of magnets means you think of a permanent magnet. When I say in external magnetic field, it means I can generate it using a temporary magnet or a permanent magnet. So when you place the same diamagnetic substance in the presence of an external magnetic field, what will happen to it? It will acquire feeble magnetization, but in which direction? In the direction opposite to the magnetizing field, because it will try to nullify the field. It doesn't want to take magnetism. It wants to repel it. So if the external magnetic field is existing like this, then inside a diamagnetic substance, the magnetic field will get generated in such a way that it will be in the opposite direction so that the net effect will get nullified. What will happen to a paramagnetic substance? It will acquire feeble magnetization in the direction of magnetizing field. Means already if there is a magnetizing field in this direction, inside a paramagnetic substance, there will get magnetic field that will get induced in the same direction, but it will be feeble. Okay. So it will acquire a feeble magnetization in the direction of magnetizing field. Then what about a ferromagnetic substance? That should also acquire in the direction of magnetic field only, but this time it will be stronger. So it will acquire stronger magnetization in the direction of magnetizing field. Am I clear with that? Then what about the third point? If you place a diamagnetic substance in a non-uniform magnetic field, what will happen to it? It will tend to move slowly. You saw that, no? When you suspend a diamagnetic substance, if this is the direction of magnetic field, then the diamagnetic substance will slowly start turning and align itself in the direction perpendicular to the magnetic field, right? So it will tend to move slowly from stronger to weaker parts. Why I told stronger to weaker parts is, if this is North Pole, this is South Pole. If this is the direction of magnetic field, then the magnetic field will be weaker in the equatorial line. So it will try to align itself perpendicular in this direction. Clear? Whereas what will happen to a paramagnetic substance? It will try to align itself from weaker to stronger magnetic field, but it will be a slow process. So that's why we are using the word slowly. Whereas a ferromagnetic substance will be instantaneous. It will be very quick. Okay. Similarly, in the presence of an external magnetic field, in the presence of a uniform magnetic field. So try to understand the difference. If they use the word non-uniform magnetic field, you don't generally use the word as perpendicular or in the direction. Because for non-uniform, there is nothing like perpendicular or in direction, because the field lines are going to be in this way. For this, what perpendicular or parallel you are going to define? It's a curve. Am I clear with that point? So what you should use is, when non-uniform magnetic field is given, use the word as weak and stronger. Whereas if they give the word as uniform magnetic field, use the word parallel and perpendicular. Okay. So freely suspended diamagnetic material aligns itself perpendicular to the field, because perpendicular is a weaker direction. What about this one? It aligns itself parallel. What about this one? It will also align parallelly, but this will be a faster one. I hope you are able to understand the difference between these two. Right? See, though it is simple, no, I suggest you guys to write it for practice. Please write it down. Keep your book in a landscape mode. Okay, keep it in the landscape mode, prepare a table and then write it. Put it horizontally, write it. Horizontal. So take a fresh page and write it. Then write down the heading as properties of diamagnetic, paramagnetic, and ferromagnetic substances. Clear with this? Finished? No? Shall I proceed? 2 minutes, sir. Seeker. Done? So listen. The fifth property is about the susceptibility of a material. So if you talk about susceptibility, what is the meaning of it? What is susceptibility in the first place? It is the extent to which a material can get magnetized. Am I right? So when you talk about it, what do you think is going to be the susceptibility of a diamagnetic substance? First question, is the diamagnetic substance in the first place getting magnetized? It is not getting magnetized at all. So it is going to have a negative susceptibility because it is already opposing. So what will happen is susceptibility is going to be small and negative for a diamagnetic substance. It will be somewhere between -1 to 0. Am I clear with that point? Whereas a paramagnetic substance is ready to get magnetized, but is it a quick one? Is it ready to get magnetized faster? No. To some extent, yes. It will turn slowly, no? It will turn slowly. Having said that, susceptibility in this case is going to be small, but unlike diamagnetic substance, it will be positive. So it will be positive and it will be some small value. Okay, it will be a small value. Whereas when you talk about a ferromagnetic substance, susceptibility is going to be very large. It is going to be greater than 1000 itself. So if you recollect what susceptibility is, it is capital M divided by H. So what is the meaning of 1000? Even for smaller input, there will be an output which is 1000 times effective. That is the meaning. Am I clear with this point? And this is a very, very important point. MCQs can be framed based on this line. Clear with that? Next. What about relative permeability? So relative permeability means permeability of the material to the permeability of ratio of permeability of the material to the permeability of free space. Am I clear with that? So it is the permeability of material to permeability of free space. So when I talk about a diamagnetic substance, it is going to be somewhere between 0 to 1. So it is greater than 0 and less than 1. Whereas when you talk about a paramagnetic substance, it is going to be slightly greater than 1. That's it. So 1 plus epsilon means it's going to be a very small value. But the relative permeability of a ferromagnetic substance is going to be greater than 1000. Means compared to vacuum, it is 1000 times more ready to get magnetized. That is the meaning. Okay. What about the permeability value? So understand what is the difference between 6th and 7th point. 6th point is relative permeability. 7th point is absolute permeability. So when you try to compare this absolute permeability, what are you going to compare it with? You need to compare it with a known quantity. You're going to compare it with mu naught. So when you talk about a diamagnetic substance, mu is going to be less than mu naught. Whereas a paramagnetic substance, mu will be greater than mu naught. And for a ferromagnetic substance, it will be in such a way that mu is very much greater than mu naught. So what they will ask us, suppose the question is, there is a material in my hand which has the value of mu greater than mu naught. Can you identify what kind of a substance it would be? It will be a paramagnetic substance. Suppose they give you this mathematical statement that material has mu very much greater than mu naught. It is a ferromagnetic substance. So that is the way questions are formed. So they will ask, there is a material in my hand which has negative susceptibility. What kind of a material it is? Diamond. Are you able to understand? Right. The next one is about the effect of temperature. Remember, temperature can affect a parameter called as susceptibility. So these two are related. When you talk about a diamagnetic substance, it is independent of temperature. Already it is not responding. Whether you're going to increase or decrease the temperature, it is going to have the same kind of a behavior, right? So susceptibility of a diamagnetic substance is independent of temperature. Whereas for a paramagnetic substance, it is dependent on temperature. How is it dependent? Susceptibility varies inversely with temperature. Means if you start heating a paramagnetic substance, it will slowly start losing its magnetic properties. If you try to decrease the temperature, it will have more amount of magnetic property. So that is how it is. That is what you mean by inversely proportional. Am I clear with this? It is inversely proportional to the temperature. Here, temperature is absolute temperature, which is measured in terms of Kelvin. Okay. What about susceptibility? Susceptibility, correction. What about a ferromagnetic substance? Susceptibility is still going to decrease. See, whatever behavior is exhibited here, here also you'll have the same thing. But there will be a slight difference. What is going to happen? This is a very strong, there's a material which is ready to get magnetized faster. Means to make this material lose its property, we need to supply more amount of temperature. So what will happen is susceptibility will decrease with temperature in a complex manner. How is it going to happen? It is almost similar except the fact that you have T minus Tc, where the Tc is called as Curie's temperature. Curie apostrophe S. Curie's temperature. Am I clear with that point? Am I clear with it? See, mostly for CBSE, they will not ask you the mathematical equations. If at all you're writing any competitive exam, these expressions would be important. Okay. Is that clear? So these are the next set of 4 points related to dia, ferro, and para. Okay. Please copy it. Done? Yep. Diamagnetic சொல்ல முடியாது, it loses its magnetic properties அவ்வளவு. Diamagnetic ன்னு சொல்ல முடியாது. Okay. Para? Superconductors. Now, superconductors as பார்க்கும்போது it was diamagnetic substance. No? You're saying that paramagnetic substance after heating it will become superconductors. Yeah, maybe, but I have to check the materials. I'm not sure 100%. எந்த மாதிரி materials நான் check பண்ணா I can give you answer. Maybe I need time for that. But it makes sense because it's going to lose its magnetic property. It should become a diamagnetic. But எல்லா மெட்டீரியல் எக்ஸிபிட் பண்ணுமான்னு எனக்கு தெரியாது. Because I've not learned about it. பார்த்துட்டு வேணா சொல்றேன். Right? So the last set of points is, see, till now we were speaking about what will happen when we place a substance in the presence of external magnetic field. Now the next question is, when you place a substance in an external magnetic field, we understood that paramagnetic and ferromagnetic substance will acquire magnetism. But what will happen as soon as you remove them? That is also a point that we need to understand. That is why the first point in this slide is going to be removal of magnetizing field. So what will happen? Magnetization. What is magnetization? It is the output. So magnetization will last as long as the magnetizing field is applied. So this material is going to get magnetized, but in the reverse direction. What about paramagnetic substance? It's the same thing. As soon as the magnetizing field is removed, magnetization is lost. But what about a ferromagnetic substance? Magnetization is retained even after the magnetizing field is removed. And that property is what we called it as? We called it as retentivity. Am I clear with this? It's called retentivity. Next. The next question is variation of M with H. So which is a parameter, which is so what is the parameter which is the ratio of M and H? What is the parameter which is the ratio of M and H? Susceptibility. So chi M is equal to M divided by H, magnetic susceptibility. So can I write this as M is equal to chi M into H? So M is directly proportional to H. Makes sense? So if that is the case, see, generally M is magnetization output, H is the input. Always remember, whenever you're plotting a graph, this should be taken on y-axis, this should be taken on x-axis. So is it not looking like the format of y is equal to mx? See, if it is of the format y is equal to mx, then you plot a graph between, listen to this carefully, if you plot the graph between M and H, if you plot the graph between M and H, then how should it look like? It should look like a straight line. But let's see are the points supporting it. Okay, listen to this. So that is the meaning of variation of M with H. What will happen is, for a diamagnetic substance, M changes linearly with H. Makes sense. M changes linearly with H. For a paramagnetic substance, also, M will change linearly with H, but there will be a certain point after which saturation is attained. So what did they say? M will change linearly with H and attain saturation at low temperature and in very strong fields. Meaning, if this is a paramagnetic substance, if I place it in the presence of external magnetic field, this will, yes, get magnetized. Okay, in such a way that what did we learn in the second point? In this, magnetization will get generated in the same direction as that of the external magnetic field. Correct? So it has susceptibility. Okay, accepted. But what will happen is, as you keep increasing this external magnetic field, the magnetic field getting generated inside this material will also increase. How will it increase? It will increase linearly. But after a certain point, beyond a point, if you try, how much ever you try to increase the value of external magnetic field, this will not have any magnetization beyond that. Meaning it has taken its maximum capacity. Beyond that, you cannot magnetize this material. That is the meaning of saturation. So now read this point, you'll understand it better. What did we say? M changes linearly with H and attains saturation at low temperature and very high fields. What is the meaning of very high fields? As you keep increasing the field, after a certain point, you cannot magnetize that material. Whereas ferromagnetic substance, which is expected to behave the same as that of a paramagnetic, see what will happen. For a ferromagnetic substance, M will change with respect to H non-linearly. M will change with respect to H non-linearly, and this will also attain saturation. So the meaning of it is, the meaning of linear and non-linear, I'll explain it. Listen to this carefully. If I take this to be H, if I take this to be M, if something is varying linearly, the meaning of it is, if I give 1 unit of input magnetic field or magnetizing field, 1 unit of magnetization is generated. Similarly, if I increase it to 2, there will be 2. So it is in proportion. It is in proportion. Not necessary that if it is 1 here, 1 here. See, for example, if it was 1 here, if it was 2 here, then if it was 2 here, what should this value be? It should be 4. It should proportionally increase. That is the meaning of linear. Whereas with a ferromagnetic substance, what will happen is, the graph is not going to be a straight line. Rather, the graph will look like this. Why this is happening is because ferromagnetic substance has very good permeability. Am I right? It has very good permeability and susceptibility. What was the susceptibility of it? What was the susceptibility of a ferromagnetic substance? It was greater than 1000. It was greater than 1000, meaning a small value of input is enough to get it magnetized faster. It is like a camphor. Even little bit of fire it'll catch the fire faster, no? Same logic. Little bit of external magnetic field will also magnetize a ferromagnetic substance to a greater extent. That is why the graph got bent more towards the output. Means you can generate more output for lesser input. So this is a very, very important point. Am I clear? Am I clear with this point? So what they can do is, they can give you this kind of a graph and ask you what kind of a material is this? Or they can give you this graph, this graph, this graph, and none of these as options, and ask you to find out which is the right graph for a ferromagnetic substance. This is where the confusion will start. For ferromagnetic, you read that it is non-linear. So what you will do, you will eliminate the first option and none of these. Confusion will start between these two, because both are non-linear. So what is that you need to have in your mind? Will the graph be bent upwards or downwards? It should be bent upwards, because when it is bent upwards, it means that more output is generated for lesser input. So the right option should be this. Am I clear? See, I'm trying to frame as many questions as possible that can be asked. And if I set the paper, that is how I'll question. Okay, that is why I'm trying to ask you. I hope you're able to understand. Clear? So first, make a note of these 2 points. Let me know once you're done with this. Have you done? No, I'm asking only the first 2 points. First 2 points are done? Okay. So, see, the next point is about the hysteresis effect. Okay, it's called as hysteresis. The meaning of it is there will be some lagging. So you can also call it as lagging effect. Okay. So what the meaning of this lagging is? How fast, listen to this carefully, okay? How fast a magnetic substance is responding to the external magnetic field, both in positive direction and negative direction. Okay, let me explain that. Let's say there is a substance that you have in your hand. Okay, irrespective of whether it is dia, ferro, or paramagnetic, there are 2 ways in which I can make this material get magnetized and demagnetized. So what do I mean by demagnetized? If I have given magnetization to this material, I need to remove that out. So which material will need that? This material, no? Because ferromagnetic substance, what does it have? It has retentivity. It can retain magnetism. Whereas these 2 substances, how are they responding? As soon as you remove the field, they lose their magnetism. So if I take this material, let's say in the first place, I'm connecting I'm placing it in a magnetic field in such a way that the magnetic field is in this direction, which is magnetizing this. After some time, what I will do is I will reverse the direction. What will I do? I'll reverse the direction. So when I connected in this direction, right, when I placed it in such a way that the magnetic field was in this direction, this got magnetized. When I reverse the direction, what should happen to this? It should get demagnetized, right? So depending on how fast or slow this is going to happen, we call that effect as hysteresis effect. I'm not going deep into it. Okay, I'm not going deep into it. Listen to this carefully. So what do I mean by hysteresis effect? Here, B, what does B stand for? Magnetic induction. So what will happen is, here, the magnetic induction vector does not show any hysteresis. Meaning, as soon as you place a diamagnetic substance, the presence of external magnetic field will get magnetized. As soon as you remove it, it will get demagnetized. So there is no lagging. Similar is the case with respect to paramagnetic substance also. Whereas for a diamagnetic substance, what will happen? It will show some hysteresis, meaning there will be some lag between the way you give input and the way you expect the output. Are you able to understand what I'm saying? So when you magnetize, so first, this is a ferromagnetic substance which has nothing inside it. It is not magnetized at all. I've taken an external magnet, connected to it. I left it for 5-10 minutes. After that, I remove the magnet. What I can observe is this material, if I take it closer to other magnetic substances, it'll start attracting. Remember, there's not a magnet at all, but it acquired magnetism from that external magnet. Now, for the magnetism that was acquired by this, for it to get lost, it will take some time. So if you need to make it lose faster, what you're supposed to do is, you need to take another magnet and connect it in the reverse direction. When you do that, you're changing the direction of external magnetic field. Okay. So what will happen is, once it acquires magnetism, no, after that, all that happens will be a lag. Means when it attains magnetization, when it attains magnetism, to get it removed, you need to do some extra work, right? Where if you try to draw a graph, no, the graph will never be a linear graph, it will be curved completely. So that lagging that is happening between the process of magnetization and demagnetization is what is called as hysteresis effect. And that hysteresis effect is seen only for ferromagnetic substances. Is the point clear? See, I've explained only the outline. Okay, one point to be stressed upon, there is something called as hysteresis loop, which is not there in your syllabus. But that word is important in the next chapter. In a chapter called, like in alternating current, we'll be discussing about something called as transformers. In the transformers, you will learn about this effect. So you need to understand. Am I clear with that point? Right. So this is an important point to be understood. And lastly, it is simple. The next two are only examples in the physical state. If you talk about a diamagnetic substance, the physical state of it can either be a solid, liquid, or a gas. For a paramagnetic substance, you can think of a solid, liquid, or a gas, but for ferromagnetic substance, they are mostly solids only. So ferromagnetic substances, they have the physical state only as solids. And the last point is, if you look at some examples of diamagnetic substances, they are bismuth, copper, lead, silicon, nitrogen, water, and NaCl. All these materials, they do not have any unpaired electrons. Right? Whereas when you talk about a paramagnetic substance, what is going to happen? Aluminum, sodium, calcium, oxygen, CuCl2. This is there. So these are all the materials which are paramagnetic in nature. Then what about the ferromagnetic substance? Iron, nickel, cobalt, these things. Right? We have something called as alnico. Any idea what it is? Aluminum, nickel, and cobalt. So it's an alloy. So you can have, these are all the examples of ferromagnetic substances. Right? So am I clear with this? So with this, the chapter is over. Okay. So for hysteresis loop, what I'll do is I'll give you a pre-recorded video. I'll not waste time in explaining it to you. I'll give you a pre-recorded video in the app. You can have a look at it. So Ama. Yeah, under temperature it exhibits that property. That is a property of nitrogen. See, generally when you take a material, you take it at a standard temperature and pressure. I hope you guys could understand, right? The importance of the stable. Those who are online, could you understand?
Yes, sir.
Is there any doubt?
No, sir.
No, sir.
Just make a quick note of it. Written duty, and the 9th point, the answer. They do not have anything. So lag எப்போ வரும் உனக்கு? So ஒரு மெட்டீரியல் மேக்னடைஸ் பண்ற கரெக்ட்டா உடனே டீமேக்னடைஸ் ஆகல அது. அதனால there is a lag between the input and the output. அதனால தான் கிராஃபை பார்த்தனா கர்வ்டா இருக்கு. It's not a straight line. And hysteresis loop வரையும் போது என்ன பண்ணுவோம்னா we take B on y axis and H on x axis. For 10th point இருக்குல 10th pointல what did I take on y axis? M and H இல்ல. ஆனா hysteresis எடுக்கும்போது we take B and H. அதனால தான் அங்க B வெக்டர் கொடுத்திருக்காங்க. B is the induction. புரியுதா நான் சொல்றது? Okay. So prepare well. So Monday I'll start with the 6th chapter. அதுல கொஞ்சம் இதெல்லாம் இருக்கும். How do you say mathematical derivations எல்லாமே இருக்கும்.
Thank you, sir.
Those who are online, if you have no questions, you can leave.
Thank you, sir.
Yeah.